Uh, this is again a centrifugal for question number 3. A centrifugal air compressor running at n equal to 1440 rpm, handles at 101 kilopascal is P1 and temperature 20 degrees centigrade. And this here 101 kilopascal 20 degrees centigrade is compressed to a pressure of 6 bar, but it is compression is isentropically. So the compression is asymptotic. Delivery pressure is 6 bar. The inner and outer diameter of the impeller are 14 centimeter and 28 centimeter. D1 and D2 is given 14 and 0.414 meter and 0.28 meter. Okay, 14 centimeter and 28 centimeter respectively. The width of the blade at inlet. The width of the blade means B1. B1 is given 0.025 meter. The width of the blade at inlet. The blade angles. Blade angle means theta and phi. 16 degree and 40 degree. The blade angle is theta is 16 degree and phi is 40 degree. Okay. Calculate first mass flow rate. We have to calculate for mass flow rate. Rate of air. Degree of reaction. Power. What is the power input to the compressor for this compression? For 101 kilopascal to 6 bar. And what is the width of the blade? Okay. What is the mass flow rate of air? So first we draw the velocity triangle, combined velocity triangle. Okay, in the combined velocity triangle, you know d1 d2. So we know u1 equal to pi d1 n by 60, u2 is equal to pi dn by 60. You know because n is given, na? N is yes, n is given, d1 is given, and d2 is given. So we can calculate u1 equal to pi dn by 60, u2 is equal to pi d2 n by 60. Okay, you know u1 and u2. Okay, so by graphical method you can draw this. First you draw the by taking scale. First you draw the u1, this u1. Make a draw a vertical line. We don't know the v1. We don't know the v1. Draw the vertical line from this point, and theta is equal to given 16 degree. Blade inlet angle is 16 degree. So we draw a inclined line. This is the inclined line. This is the vertical line, and this is intersect at this point. So for this point we get VR1 and V1, and V1 is equal to Vf1 is equal to Vf2. Okay, in that manner you can draw the inlet velocity triangle. Now you can also draw the outlet velocity triangle. Okay, you can also draw the outlet velocity triangle. Okay, for that phi is given. Phi is given 40 degree. Okay, so from this point draw the 40 degree line. From this point draw a 40 degree line. This line intersect at this point. This point is intersect at this point. So we get VR2, and okay, from at this point we get the VR2. Okay, and you know the V2, U2. So from this point to this point to this point, you know the U2. Okay, and then join this point and this point, we get V2. Okay, so all these angles, theta, pi, alpha, beta, and this is the complete combined velocity triangle for centrifugal air compressor. And then we measure VW2, VR1, VR2, and VF1. V1 equal to VF1. These are VW1, VW2, VR1, VR2, and VF1. These are required for the calculation process. Okay, calculation purpose. So first we find out work input per kg of air. Work input per kg of air is Euler's work, because actual work is not given. T2 T1 is not given. So U2 into VW2. Okay, this is meter per second. This is meter per second. So we can put the values of U2 and VW2. U2 pi d2 n by 60. VW2 we get from this diagram. 70 we get the input per kg of air, that is 369.9 joule per kg. And now this is meter per second. This is meter per second. You will see the unit 1 joule. 1 joule per kg is equal to, what is joule? Work, that is force according to second law, Newton's second law, that is mass into force into sorry, first we write joule. 1 joule equal to 1 Newton meter. 1 joule equal to 1 Newton meter divided by kg. What is 1 force? 1 Newton. 1 Newton is equal to 1 Newton. Sorry, 1 Newton. This 1 Newton is in the denominator. 1 Newton equal to mass into acceleration. That is kg meter per second square. Okay, this Newton is cancelled. Kg is cancelled. Okay, we get m square, meter square upon second square, means 1 joule per kg is equal to 1 meter square per second square. If we multiply by joule 10 to the power 3, that is kilojoule, and this is 10 to the power 3. So 1 kilojoule per kg equal to 10 to the power 3 meter square per second square. This is very important equations. Okay, so we get work input per kg of air, that is 369. First we find out the mass of air. First we find out the mass of air. So for mass of air, simple formula, rho 1 A1 VF1. Okay, for that D1 is given, blade width B1 is given. Okay, so rho A1 VF1, and what is A1? Pi D1 B1. So first we calculate rho 1. So what is rho 1 is equal to initial pressure and temperature is given statically P1 upon RT1. So P1 is given, R is given, T1 is given. Put the values and we get 1.201 kg per meter cube. So this is one rho 1 pi d1 is given, v1 is given 0.025 meter, and vf1 how we calculate from the combined velocity triangle. Vf1 is 3. So we get the first answer. Mass flow rate is 0.0396 kg per second. Okay, this is the mass flow rate required for centrifugal air compressor. Okay. Now power input to run the compressor. Power is equal to m dot into the work done. Work done, Euler's work you calculated U2 into W2 multiplied by this mass flow rate. We get the power input to the compressor, that is 14.61 watt. Okay, if this is joule per second, joule per kg, then you add. If it is in kilojoule per kg, then it is kilowatt. Okay, and now the third one is degree of reaction. Degree of reaction, the formula is U2 minus VR2 square plus VR1 minus U1 square upon 2U2 VW2. These are all values we will U2 and U1 will get pi d1 n by 60, pi d2 n by 60. Okay, we will get these values. Okay, and VR2, VR1, VW2 we will get from the combined velocity triangle. If you put all these values in degree of reactions, we get degree of reaction is 58.64%. 58.64%. Now we find the last one, the width of blade at outlet. And for that, we are in centrifugal compressor we are assuming that Vf1, where Vf flow is constant. The Vf1 is equal to Vf2 equal to 3 meter per second. Now the air is compressed asymptotically. So here is the diagram. 1 to 2s is asymptotically and 1 to 2 is polytropically. Now in this problem, it is given the air is compressed asymptotically. So the final process is 1 to 2. If the air is compressed polytropically, we can write 1 to 2s asymptotically, and final process is 1 to 2. Now in this problem, the final process is also 2 only, because it is compressed asymptotically. Air is compressed asymptotically. So here is 1 to 2. You can write s also, 2s also, no issue. Okay. So therefore, we can also write 2s. T2s by T1. If you have any problem with these two, you can write 2s. Okay. So T2s by T1 equal to P2 by P1, gamma minus 1 upon gamma. We know the value of delivery pressure, suction pressure, it is given in the problem T1. So we get T2s. Okay. Now pressure is also changing for inlet outlet. So density also changes. So the rho 2 is equal to P2 upon RT2. So we know the value of P2, RT2, this is given in the problem. Sorry, T2 is this. Okay. Put the value of T2 is here. Okay. And we get density of air, and again we are using curtain mass flow rate at outlet. This is rho 1 A1 F1, this is the mass flow rate at inlet, and rho 2 A2 F2, it is mass flow rate at outlet. So this is rho 2, we just calculated. What is A2? Circumference into width pi D2 into B2 into F2. Putting the values of mass flow rate, V rho 2, D2 and Vf2, we get the width at outlet is 0.0035 meter, or we can say 3.5 mm. Okay, this is simple problem. Here is only just put the formulae. Okay, means mass flow rate and degree of reaction formula, work done formula, again mass flow rate formula at the suction conditions or inlet conditions. Okay, we are going to first work input. The only difficult part is small, just you to draw this diagram. If you know this diagram and know the formulae, you can solve it easily, this problem. Okay, it is very easy problem. Okay, from this diagram you must know the VW2, VR1, VR2 and VF1. So these are the values required for calculation purposes. Okay, so this is very simple problem. Okay, now we will see the problem number, question number 4.